Gauss's law, integral around a closed surface of E dot dA equals Q enclosed over epsilon naught. Now you know it. We've played with it. We've thought about fluxes on this side. We've thought about the charged enclosed. We've written fun homework problems relating the two. And that's really good stuff. I mean, I could do that for a couple days and not get bored. That's good. But it's really not what Gauss's law, it's really not the big powerful thing Gauss's law can do. What Gauss's law is really good for is calculating the electric field. And that's not obvious from looking at the equation, because the E field is buried in this surface integral, this big vector calculus mess. You can't solve this for the E field in terms of writing E equals. Right? But it turns out it is actually very powerful for finding the E field, but to do it, you have to really understand how the vector calculus works. Okay? So let me show you how that works. We are going to do Gauss's law for a point charge. So we're going to use Gauss's law to find the E field. All right? So the charge, it's not really a point. It's just a small charge that I've been drawing the whole time, a little plus Q. Okay? So the first step in using Gauss's law to find an E field is to draw a Gaussian surface. All that means is the closed surface over which you're going to apply Gauss's law. In addition to naming the law after Gauss, they name the surface after Gauss. That's all it is. It's nothing special. It has to be closed, is the one special thing. And choosing the Gaussian surface is the most important part of this. If you choose the right one, it'll be fine. If you choose the wrong one, it won't work. So knowing how to choose the right one is a little bit of wisdom. Okay? We can't write a formula for everything you need to know how to do in physics. There is a little bit of experience and wisdom involved. And the wise person would tell you to use symmetry. Okay? So first I'm just going to give you the surface. I'm going to talk about why we chose it. And then you'll get some experience and you'll see how to find the right symmetry. So in this case, it's a sphere centered on Q with radius R. Okay? So let me draw such a sphere around Q like this, like that. And it's a three-dimensional sphere. It's a three-dimensional surface going around Q. Okay? And it has a radius R. That's our Gaussian surface. So now we have to come over here and apply Gauss's law. So the right side is not too hard. That's the plus Q is the charge enclosed over epsilon naught. But we also have to do the left side. Okay? We have to think about the surface integral. So what we rely on is symmetry. This surface was chosen because it has a symmetry that matches a point charge. So symmetry of our Gaussian surface is going to tell us two things. First, we're going to use it to deal with this dot product. This dot product means we have the E field vector and the dA vector. We take the dot product of those two vectors. So it turns out everywhere you go on a sphere, dA sticks out, right? So if we were to tile this up like the disco ball into little squares, every little square we would draw the dA sticking normal to the surface. So dA is like that, dA is like that, dA is like that, sticks out. But also due to symmetry, the electric field would always stick out. Okay? And that's a little bit trickier to see just based on symmetry. Basically what I'm doing is I'm using Gauss's law to derive Coulomb's law. And you may say I'm cheating. You may say, well, you're assuming Coulomb's law by saying which way the E field points, but I'm really not. I'm really using symmetry because forget all the surfaces there, forget the whole universe is here. Well, don't forget the universe here. Forget the whole lecture hall's here. We have a charge at one position and we have a point at another position. They're on an axis, the line between them. And you ask yourself, which way is the E field going to point there? And the answer is due to symmetry, it could only point this way, away if it's a positive charge, or it could possibly point that way if it's a negative charge. But it can't point any other way because there's no reason for it to point any other way. It can't have a component this way because there's nothing special about this way. The charge is here. If you gave it a component this way, there's no reason you couldn't give it one that way. Right? The symmetry tells you you can't have sideways components because the charge looks the same no matter where you go around that axis. So really, it has to be due to symmetry that the E field always sticks out. And that's true anywhere you go. Due to symmetry right here, the E field has to stick out. And due to symmetry right here, the E field has to stick out. So due to symmetry of a sphere and the charge being at the center, E is always parallel to dA. Okay? And that rule lets us simplify the integral a little bit. It lets us say it's the integral around a closed surface, and now that we know that E is parallel to dA, that means the angle between them is 0 and the cosine of 0 is 1. Really, we're talking about their magnitudes of E, the magnitude of dA, and then the cosine of 0 is 1. So you just leave it there, or you don't write it. There's a 1 there. So what we've done is use symmetry and the fact that these two are parallel to take out the dot product. Okay? But we're not done. We still can't do this integral because we have to integrate over the area, and what is E doing? E could be a function of area. So we have to go a little bit further. What else can symmetry tell us about this E field on the surface? It can tell us about the magnitude. Symmetry also tells us that E magnitude is constant on the surface. And why? Because anywhere you go on the surface, if you're right here, you're a distance r from the charge. So you're going to have some E field. If you're right here, you're a distance r from the charge. If you're right here, you're a distance r from the charge. Anywhere you go physically is no different from any other place you go. So there's no reason that the E field would change. There's nothing special about this place relative to this place. They're all the same place. So the E field has to be the same everywhere you go. If the E field's the same everywhere you go, you can take it out of the integral. Okay? So now we have the E field magnitude times the integral around the surface of dA magnitude equals Q over epsilon naught. Aha! Now that it's out of the integral, we can solve for it. Right? We can now solve for the magnitude of E. And actually this integral now became not so hard. It's just the integral of dA over a surface. You don't even have to write it in any fancy coordinates. It's just the area of a surface. Okay? So now we could write it like this. We could say the magnitude of E equals times the area of a surface of a sphere, 4 pi r squared is the area of a sphere, equals Q over epsilon naught. All right. And now the big ending, I've left myself no room. I'm going to write it on here. It's so exciting. I'm going to put it right here. Is that the magnitude of E equals 1 over 4 pi epsilon naught times Q over r squared. And that's Coulomb's law. If you're obsessed with Coulomb's constant, remember this is Coulomb's constant. Ke is just the convenient way to write 1 over 4 pi epsilon naught. And it's easier to remember because it's 9 times 10 to the 9. But this is how you'll see it in a lot of books. 1 over 4 pi epsilon naught, Q over r squared. It's just the magnitude of the electric field. The direction we actually know from symmetry. So it doesn't fully look like Coulomb's law because we aren't doing it as a vector. But I could just say by symmetry, I could make it a vector that way, by symmetry. So that's an example of how we used Coulomb's law. Even though the electric field is stuck in this vector calculus formula, we used symmetry to get the magnitude of the electric field out. And it actually gave us the electric field everywhere because we did it for one radius, but it would be true for all radii. There's no special radius where this is true. It's symmetric for any radius. So we actually got a general solution that's true, in this case, in all space, in all radii spherically symmetric around the point charge. So you see Gauss's law is actually very powerful. You can calculate many E fields in many situations, and we're going to cover a few of them.
Good morning, everyone. Dr. Hafner was called away for an important mission at the San Diego Comic Book Convention, so I'll be giving a guest lecture today. My name is Professor Nadelson, and we are going to be talking about finding the electric field from a line of charge. Now, I know Dr. Hafner has already shown you how to use Gauss's law as a way of figuring out the electric field from a point charge, and we are going to expand on that and work with, instead of the zero-dimensional case of a point charge, we're now going to do a line charge, and then later on in the course, you're going to learn how to deal with a two-dimensional sheet of charge. So, a line of charge. Here is some rod or line, and we'll talk about how far it extends in either direction in a moment. But the idea is that somewhere out here, we're interested in the electric field produced by this line of charge. And we characterize the line of charge by a charge density, a linear charge density lambda, which has units of coulombs per meter. So obviously, if I have twice as long a line, I have twice as much total charge. Now, what you learned when talking about Gauss's law is this idea that I can have some closed surface, and I'm going to take this closed surface, and over that surface, I'm going to perform an integral of the electric field at whatever little spot I am on the surface, dotted with a little piece of surface, and the vectorial direction is given by a little unit vector that's normal to the surface there. And if I'm able to do this integral, what Gauss's law says is that I do this integral over the whole closed surface, and this ends up equaling the enclosed charge, and to get the units right, in SI units, it's the enclosed charge divided by epsilon naught. Now, the trick then, as Dr. Hafner has already alluded to, is that we need to figure out some clever way of picking a surface so that we can use symmetry to find the electric field without doing a whole bunch of really complicated geometry. Physicists, as I'm sure you've seen from Dr. Hafner, are just as lazy as anybody else, and what we want to do is make the problems as simple as possible. So we want to choose a geometry for our calculation that uses the symmetry of the problem. So you would not pick a surface that looks like a giant Mickey Mouse or a balloon or something strange. When you have a line of charge, there's a natural symmetry associated with this line of charge. And so it's very tempting to choose a cylindrical geometry of some kind because there's cylindrical symmetry about the axis of this line of charge. So you could imagine picking some kind of a surface. In fact, I will use a different color. You can imagine picking some kind of a surface that looks like that, where despite my crude drawing, you're supposed to believe that the line of charge actually goes down the axis of the cylinder. Now, you can think to yourself then that the idea is we're going to somewhere pick a patch of cylinder, and so here's some little patch of cylinder up on the sort of the northernmost part of this surface, and there's some unit normal associated with that piece of area, and for simplicity, I'm going to have it point up because I'm really right on that top bit. And then we're going to basically figure out whatever the electric field is at this spot, and we are going to do, suppose the electric field pointed like that, if that was E, and then this little yellow arrow was dA. We're going to do this over the whole surface. We're going to take E dot dA everywhere and add it all up, and then we will set the result of that. If we're careful about keeping track of our closed surface, we have to define the ends of our cylinder too. Then we will know how much charge is enclosed, and we will in fact be able to do something very clever because of symmetry and basically pull the electric field out of the integral if we set our geometry up properly. And we can have an expression for the electric field as a function of position, at least the magnitude of the field. So I've drawn here sort of a very general case where I'm at no particular point relative to the ends of the line of charge, and so my electric field doesn't necessarily point nicely along the same direction as dA. If we really want to deal with the finite line of charge, it's possible to do that. You've seen already an example with using symmetry where if you pick yourself to be in the exact center of your line of charge, you know that the electric field has to point radially outward from the line because that's the only direction in the problem, basically. That's the only symmetry direction that makes sense. If we want to be really lazy, or we want to make a very simplifying approximation, let's assume that this line of charge is infinite. Let's assume this line of charge or is at least extremely long compared to any other scale in the problem. So let's extend this line of charge back here to negative infinity, and out here to positive infinity along, say, the x-axis. If we do that, then now where we put our surface left and right doesn't matter because wherever we are, there's an infinite amount of charge to one side and an infinite amount of charge to the other. So we're always in a nice symmetric situation. And if we have, again, the axis of the cylinder along the same line as this line of charge, then we have a perfectly radially symmetric problem. And so wherever we are, wherever we draw some little piece of surface, the surface normal is going to point radially outward, if we're on that outside surface of the cylinder, and the electric field, whatever it is also going to point radially outward. And that's really nice and simple because it means that the E field dotted with dA just becomes a regular product of their magnitudes. We don't have to worry about the cosine of the angle between the two vectors. We just are able to multiply the magnitude of the electric field times, in this case, 1 for a unit normal, times a little piece of area. So what we're going to do then is actually try and figure out how to make a closed surface. I haven't said anything about the ends, about the end caps of my cylinder. We can make our cylinder whatever length we want. If we want to make life simple, we will just say that this distance here, this length, is some delta x. All right, and we can talk about the surface area of the end caps, but we don't even have to get very fancy for this, because we know what direction is the electric field going to be pointing. If we have nice flat end caps for the cylinder, the electric field is going to be pointing radially outward from the line of charge. And our little surface normal for a little patch of area on one of these end caps is going to be pointing, in this case, in the negative x direction. If we were on the other side, it would be pointing in the positive x direction. And we can just look at this and see by inspection that on the end cap, E dot dA is 0 because E is perpendicular to dA. So that's nice. It means we can write down our full expression for our closed surface in 3 pieces. We can worry about the left cap, the right cap, and the surrounding wall. And we can write it as a sum of those 3 terms. So let's do that. So we're going to take this integral over a closed surface and write it as a sum of integrals over patches that make up that closed surface. And so we're going to then have integral of E dot dA over left end plus integral of E dot dA over the right end plus integral of E dot dA over what I will call the wall, right? That's our full integral over the closed surface. And I just told you that that has to end up equaling the enclosed charge divided by epsilon naught. How much charge have we enclosed? I told you we were dealing with a segment of this line that was of length delta x. So the enclosed charge over here is going to be lambda times delta x. All right, and then of course we've got the epsilon naught down below to get the units correct. Now, I just told you that on the end caps, on either the left or the right end cap, E dot dA is always 0 because the surface normals point along the plus or minus x axis, and the electric field points radially outward, which has to be somewhere in the yz plane. So that means we can say that that is 0, and that is 0, and now we're just left with this piece. So let's sit at some distance r, little r, away from the axis, actually, not away from the edge of my little finite diameter rod of charge, but we're going to sit some distance, little r, away from the axis. So when we do that, we're going to say that the electric field is basically going to be, because of symmetry, since we're always the same radial distance away from the axis, the electric field all over this whole surface is going to have the same magnitude wherever we are. It might vary in direction. It will vary in direction because it has to point radially. But wherever we are along this whole surface, the electric field has the same magnitude, all right? And that's the thing we want to find. And again, the surface normal is always going to be in the same direction as the electric field. So what we're going to do is we're going to have the electric field, the magnitude of the electric field. We're going to evaluate this integral here. It's going to be the magnitude of the electric field, which we're able to pull out of the integral because it's constant over the whole surface, times the surface area, the total surface area of the wall of this cylinder. And we all know what that is. That's going to basically be the circumference of the cylinder. So that's going to be 2 pi little r. That is our distance away from the axis. That's the circumference of one hoop, if you will. And then the surface area is going to be that circumference times the length. So then we're going to have a delta x. So electric field times 2 pi r times delta x has to equal lambda times delta x over epsilon naught. And as often happens when we're clever about how we set up our physics problems, our surfaces in these Gauss's law problems, we find that the delta x goes away, all right? And we can, it cancels out, and we can move the 2 pi r over to the other side, and then we find that the electric field, the magnitude of the electric field, the direction is always going to be radial, but the magnitude of the electric field at some distance r away from the axis, away from the line of charge, is going to basically be lambda over 2 pi epsilon naught r. And that is sort of our big result that we were going for. And again, vectorially, this is a radial electric field. So if you wanted to, you could stick a vector sign here and put a little r hat, a little unit vector pointing in the r direction to give you the complete expression. Now this is nice. It shows that we can make a general formula. We can arrive at a general result from considering a specific case. That's also something that you'll see over and over again in this course. As physicists, we like to be able to do this. Now, we're at whatever radius we are from a uniform line of charge, we know what the electric field is. We've sort of solved the general problem. One thing, two more things I want to point out, rather. One is that, as you can see, the electric field drops off as you move away from the line of charge. This makes perfect sense. You know from a point charge, the electric field drops off like 1 over r squared. Now we have, from a line charge, the electric field drops off more slowly. It drops off like 1 over r. And the other thing I wanted to point out is that as you get very, very close to the axis, assuming we have an infinitesimally skinny line of charge, assuming that the little diameter I drew here is actually very, very, very small, as we get very, very close to the axis, the electric field can get very, very large. Now, in a real system, if I actually had a true line of uniformly charged wire or something like that, this expression would obviously no longer apply once I tried to go kind of inside my wire. But for the mathematical idealization that we like to deal with, where my line of charge is infinitesimally tiny, then this works. And what you see is that the electric field actually would blow up if you got to the axis. So that's it. I think this is the main result we wanted to arrive at. And I think in future sections, you're going to learn about how to deal, for example, with a sheet of charge.